Free body diagrams. This is our second video on free body diagrams. I'll spare you the speech of how important this is. I figure since you're here watching the video, you know that. Alright, let's get to it. We've got two masses. This time they're touching each other and they're on a frictionless surface. We'll just keep it simple for now. And you're pushing on one of them and trying to move them across the frictionless surface by pushing on one of the masses. So we're going to do free body diagrams for both of these masses. Let's start with M1. And we represent our objects with a dot because we're just dealing with point objects right now. Later on in the quarter, they'll have some dimension to them. But right now, we just deal with everything as a point object. And the first thing we want to do, right, remember our free body diagram shows all the forces acting on M1. And so what we want to do is look and see what is touching M1. And the first thing I see that's touching M1 is U, right? This force, F. And that's pushing it to the right. So I always like to have the tail of my vector on the dot and the vector going in the direction it points. So there's the force. It's on M1 and it's from the person. The other thing that's touching M1 is the ground. And a surface can interact in two ways. It can interact parallel to the surface through a friction force, but we don't have any friction in this problem. And it can interact normal to the surface, or perpendicular to the surface, through a normal force. And so I'll draw the normal force in. Again, I always put the tail of the vector on my dot. And this is a normal force. We usually use N for normal force. And this is on mass 1 due to the ground, I guess. And the other thing that's touching M1 is M2. So we've got the force taken care of, we've got the ground taken care of. M2 is also touching M1. Now, again, surfaces can interact in different ways. They can interact through a friction force, but we don't have any friction force here. They're just butted up against each other. And they can interact with the normal force. So M2 is pushing to the left on M1. So I'm going to draw a vector pointing to the left. I'm going to call it a normal force because it's a surface pushing on M1. This is a force on M1 due to M2. So those are all the things that are touching M1. Now the only thing we know of right now that can reach in from a distance and exert a force on M1 is gravity. So I'll draw that in here now. That points to the center of the Earth, and we usually call that weight because that is the force of gravity on M1 is the weight of M1. That's a force on 1 due to the Earth. And I think that completes my free body diagram for M1. Now I'm going to do my free body diagram for M2. I'll draw M2 as a dot. And what's touching M2? Well, the first thing I see is the ground. The ground can interact, that's a surface, it can interact through a friction force, which we do not have, or a normal force. So I'll go ahead and draw the normal force on M2 due to the ground. The other thing that's touching M2 is M1. And again, there's no friction because they're just pressed up against each other in this case. And so all we have is a normal force. There's a normal force pushing on M2 to the right. And that's on M2 due to M1. And that's everything that's touching M2. And the only thing that can reach in from a distance is gravity. That's the weight of 2 due to the Earth. So I'm being very careful to put these double subscripts here because we're just learning. As you get quicker at this, you can just put a single subscript to differentiate normal forces. For example, in my free body diagram for M1, I have a normal force. In my free body diagram for M2, I have a normal force. And those two normal forces are different. So don't call them both N. If you call them both N, They better be the same. You're going to make a mistake. Call one N1, call the other one N2. If they're different, make sure you note them as being different with different subscripts. Okay, so at this point, I want to take a quick look at Newton's third law pairs. And what we see is that there's only one third law pair here. We've got a normal force on 1 due to 2, and we have a normal force on 2 due to 1, and that's an interaction. Those are equal and opposite forces due to that interaction between M1 and M2. And so they're a Newton's third law pair. We know that the magnitude of those two normal forces is going to be the same. There are no other third law pairs. You cannot have a Newton's third law pair within one free body diagram, because all the forces in one free body diagram are the forces on that object. And a Newton's third law pair is the force on one object and the force on another object that's interacting with it. So you have to be in two separate free body diagrams. If the weight on one is a Newton's pair with something else, it would have to be with the Earth. You'd have to have a free body diagram for the Earth there with the force on it due to mass 1, and then you could have a Newton's third law pair. But it's not a Newton's third law pair with a normal force. That's a common misunderstanding. So that concludes our free body diagrams for this situation. We'll look at another one in video 3.